So today we're doing Unit 4, Lesson 4. We're going to be covering an introduction to chemical reactions. Unit 5 is actually going to be all about chemical reactions. You're going to learn how to predict the products for many different types of chemical reactions. You'll learn about specific types of chemical reactions. I think I've told you all before, but I'll tell you now. Quarter 3 is usually the most difficult quarter in the course because it's got that unit in it, and it's also got math in it, the quarter 3 material. So you want to make sure end quarter 2 on a strong note with a high grade in the class. That doesn't mean you won't do well in quarter 3. I'm just saying that quarter 3 will be the most difficult of the quarters of this class. It's just that's where the heftiest material is, and this class builds just like a math class does. So if you don't understand topics from earlier in the year, it's going to come back and hurt you later on in the year. So just so you're aware, make sure that you are looking back over things like polyatomic ions, recognizing them, because they are going to show up today. All right, so Unit 4, Lesson 4, Introduction to Chemical Reactions. You watched the Khan Academy video just to kind of warm up on what a chemical reaction is. We're going to go over some intro terminology, and we're going to learn how to do something called balancing chemical reactions today. So let's go ahead and get started. Unit 4, Lesson 4, Intro to Chemical Reactions. As always, you want a handy-dandy periodic table. You should always have one on you. We'll be referencing back to that as we go through the lesson. We don't need it really for much of anything today except to know the chemical symbols for different elements, but there's a lot of material in here as you've seen through the year. In this unit, you were supposed to memorize this, if you all recall. Do you remember what that was? The 7? The ones that exist as? The ones that the elements exist as 2. We call those diatomic elements. That's going to come back in Unit 5. It'll actually also come up when we wrap up the intro on Wednesday. It'll come back on that day. All right, so introduction to chemical reactions. The first thing is you need to be able to tell, so everything here is important. You should write everything here down, especially the parts that's in bold and underlined. There are keywords we're looking for to know that a chemical reaction has taken place instead of just a physical change. And a chemical reaction is some kind of rearrangement of atoms or some kind of rearrangement of elements into different compounds. And so there are key things experimentally we can look for, and in a couple of weeks, we're actually going to have a strange couple of weeks because next week there's only 3 school days, and I only see you once. So in a couple of weeks, like 2 or 3 weeks from now, we will have a lab. And we just had a lab, actually, believe it or not, like last class period. But in a couple of weeks, we'll have another one where we go through and we identify different types of chemical reactions. And so these are the keywords we're looking for that tell us that some kind of rearrangement has taken place, some kind of chemical reaction has taken place. The first one is burn. Burn is a combustion. Anytime we burn something, that's a chemical reaction. And it's not reversible because we can't get back what we once had. If you throw your paper in a fire, you can't get the words on that paper back. Rot, that's a chemical change. Rust, actually a chemical change. I believe we'll be looking at that reaction later on. Decompose. Can you?
Yes.
You can scrub off the top layer, but that's still iron oxide. You've actually changed the mass, so you can't get it back. You can scrub off the top layer though. Ferment, explode, and corrode. So these are a lot of the key terms we'll be using that tell us that we have a chemical change. Some of them you may be familiar with. You're probably familiar with explosions. You're probably familiar with corrosion. Corrosion means that some kind of acid, for example, is eating into a material and disintegrating it. We'll be looking at that in one of our labs. And so these are key indicators that we have a lab. that we have a chemical reaction that's taken place. There are others that observationally you could see. And we have seen some of these already this year. If you mix two things together and you observe a color change, this tells us that a chemical reaction, some sort of chemical reaction has taken place. Potentially. If energy is released, meaning it gets hot your mixture gets hot or it gets cold. If energy goes in, actually. This can be a result of a chemical reaction. That's what AICE is going to learn about today. They're learning about energy. If you produce a gas, so some reactions you'll see steam coming out. It looks like a gas. That means you have a chemical reaction most likely that's taken place. And then the last one is called formation of a precipitate. Write that down. We're going to go over precipitate in Unit 5 a lot. But just to bring up what it is, a precipitate is a solid that forms as a result of mixing two liquids. Two liquid solutions. It means you have something insoluble is made. So just to bring up what is a precipitate, we're not going to really see too much with it in Unit 4. We'll see it in Unit 5. It's being demonstrated to you here in this diagram. If I mix two solutions together and you form a solid out of two solutions, that solid that forms is called a precipitate. And it is a solid that is insoluble. So just an insoluble, meaning not soluble in water, solid that is formed. The terminology soluble and insoluble you should now be familiar with because you did do a lesson on that. Solubility means it dissolves in water, and soluble means does not dissolve in water. In this reaction that's being shown, these were actually two clear liquids. This is one of the reactions you'll do in a few weeks. It's actually really cool to see live. But it's actually something very dangerous that's being formed because there's lead in here. And I don't know how much y'all know about lead, but it's something you're not supposed to pour down the drain. You do not want that in the water supply. But it actually makes a very pretty result when you mix two colorless liquids together. It gives you that yellow, bright yellow solid. It's kind of interesting because in nature, when you see bright colors, that typically means danger. And that can often be the case here as well. All right, so I'm just giving you some time, okay, because there were keywords and key things we're looking for to know that chemical reaction is taking place, and then we're going to continue. For what? But not everything. Bluebird. All right, so what actually happens in a chemical reaction? And you should have written this down in your introductory notes on Khan Academy. Yes. Go ahead, grab the pass is purple now for 2024. Grab the purple pass, and then just bring it back into the back. All right, so what actually happens? In a chemical change, when we see the color change, when we see the gas form, what's actually happening is that the composition of matter changes. Well, what is that? We went over composition of matter being elements or compounds. Being pure substances. A couple classes ago, actually, which is like 3 weeks at this point. So during a chemical change, the composition of matter changes. This means that the atoms rearrange in some different way. Instead of having your atoms as elements, they turn into compounds. They mix together and form compounds. They fuse together and form compounds, I should say. Or they could rearrange in some other way. And so some examples. During a chemical change, the composition of matter always changes. You could have this. This is Fe. What's that? What element is that?
Chlorine.
Nope, F.
Iron.
Iron.
I didn't see
And then
it.
O2 is
Oxygen.
oxygen. So if I oxidize iron, that's actually called the reaction of rust. And so when you rust iron, you actually form something brand new. You form a new compound. Fe2O3 is the most likely compound you'll form from this. So iron plus oxygen makes iron oxide. This is one of the types of reactions we're going to look at. It is called a combination or a synthesis because you have two elements that combine to form a compound. That's one example. Now you may be looking at the numbers and thinking to yourself, wait a second, Miss Lee. You wrote 2 oxygens on the left side and you wrote 3 oxygens on the right side. Something looking wrong there, meaning the numbers don't match. And the numbers do have to match. That's called the law of conservation of mass. You have to have the same amounts on each side. I gave you an unbalanced equation. It's called a skeleton equation, which we'll see in a little bit. A skeleton equation tells us the identities of what we have, but doesn't have the corrected amounts. So this is basically the bare bones version of it. Iron plus oxygen makes iron oxide. We'll be going over iron 3 oxide. We'll be going over how to construct these more next class, but just so you know, that's what that is. It would be 3O2, just to put the numbers in. That would make this 2 Fe2O3, because 3 times 2 is 6 oxygen, so this has to be 2 times 3 is 6 oxygen, and then that changes this to 4. That's what we're going to be doing at the end of today's lesson, is balancing skeleton equations. Basically getting the right amount. But all the equations today will be provided to you. For example, I'll give you the iron plus oxygen with the correct chemical symbols goes to Fe2O3. Another example chemical reaction is, I don't know if you all remember, I believe I did, I don't know if I did it in this class. If I didn't, you'll see it in a couple of weeks. Did I do the thing with the bright white light in this class? I can't remember if I did or not. I didn't. If you take magnesium and you burn it in oxygen, you actually form this, and I'm getting a little bit ahead of myself. And it emits a bright white light. I did it in some of the classes. I don't think I did it in this one because this is the first one I teach in. So I'll make sure to cover it in your lab that you do. But this emits a bright white light, like a flare, actually. And this is another example of a chemical reaction. You can observe flare, you can observe a color change, energy emitted. Notice how you've got magnesium and oxygen by themselves on one side, and you've got magnesium and oxygen in a compound on the other side. So the idea here is that you're going to be rearranging atoms in some way. And that's a chemical reaction. Either an element turns into a compound, or a compound breaks apart into individual elements, or you've got some other kind of rearrangement that occurs. And so there's some other vocabulary we need to get through. First of all, what is a chemical reaction? This is where our substances change into other substances. And you do have to know what is a reactant versus what is a product. So if I've got a reaction like this, let's do magnesium plus HCl goes to this. You've got to be able to look at a chemical reaction and know what are your reactants and what are your products. And so write the definitions and then that chemical reaction, and then you should identify what are your reactants and what are your products by looking at that chemical reaction. That's what you've got to be able to do. So when you're done, write this example chemical equation out. Where are the reactants and where are the products? What is the start of the reaction here? So we read it left to right. So anything before this arrow, anything to the left side of the arrow, we call the reactants. So you should identify those. Your reactants here would be magnesium, which is a pure metal, and HCl, which we'll learn shortly is hydrochloric acid. So this is a reaction of corroding, or a corrosive acid corroding a metal. And what actually happens in this reaction is there's a rearrangement. Notice magnesium is no longer by itself as an element on the product side. It's now part of a compound. And hydrogen is by itself instead. And so there's a rearrangement of atoms that has happened here. Therefore, we have a chemical reaction. If you saw Mg plus HCl on both sides of the reaction, there would be no reaction. So like if you saw Mg plus HCl and then Mg plus HCl, it's not a thing. There has to be some kind of rearrangement. There has to be a change for there to be a reaction, some arrangement of atoms that is different. And so these right here are what we would consider our products. This is the identity of our products. Magnesium chloride and hydrogen. Welcome back. And so the first thing you're expected to do is to be able to look at a chemical reaction and identify what are your reactants and what are your products. Notice that your different reactants are separated by a plus sign in symbolic form. The way we read this is magnesium and. They're separated. The plus sign separates. And here we see magnesium chloride and H2. We're going to go over other aspects of chemical reaction shortly. But the other thing to note here is that this arrow is the chemical reaction taking place. It has a name called yield sign, but it means the chemical reaction is taking place. So whatever's happening, explosion, corrosion, rotting, burning, it happens at the arrow. That means reaction takes place, rearrangement. Chemical reaction takes place, that's the arrow. The plus sign separates each of your reactants or each of your products. So here I know I have two reactants I'm putting together, and I'm making two individual products here. The type of reaction, that's going to be Unit 5. We'll learn about that in Unit 5. All right, so the next thing that's important to note, and some of you might have already thought about, because when we were talking about that first reaction with rusting iron, I told you the amounts needed to be the same on both sides. So the next thing we need to bring up is this. In any chemical reaction, it's important to note that law of conservation of mass must be obeyed. What does this mean? In a chemical reaction, you don't get something from nothing, and you don't turn something into nothing. The amount that you start with will be the amount that you end with. So another way of saying this is the amount of reactants has to equal the amount of products. And that's going to formulate the basis of most of the unit in the math chapter we have to do, is this main idea. The amount of your reactants have to equal the amount of your products at the end. Today, we're going to be looking at that in amount of atoms. If I, for example, have 2 atoms of iron on the reactant side, I have to end up with 2 atoms of iron on the product side. Remember, these are not nuclear reactions, so we're not going to be changing elements. We're going to have the same elements on both sides of the chemical reaction always. We're only going to be exchanging electrons. So you should write down the part that I circled and the part that I added, just to remind you. This has a fancy name. It's called the law of conservation of. Yeah, same idea as the law of conservation of energy, but we're talking about the law of conservation of matter, basically. And so what you'll see a lot of times in this class is we're applying laws. This is what the law is. We'll be applying it for other laws. Good to move? Yeah. There you go. All right, I'm moving forward in about 20 seconds. All right, moving forward now. So this right here, you do not need to write anything down on except on your handout. You should write Unit 4, Lesson 4 at the top, so you know where this belongs to. The handout that I gave you is double-sided. You should be on the side that says symbols used in a chemical equation. That's the side that I passed out. And these are the different aspects of a chemical reaction that you do need to know to memorize them. Most of them are straightforward, but there's a few that we just need to go over. The plus sign I already brought up. This separates each of your elements or your compounds. The arrow is the actual chemical reaction happening. It has a fancy name. It's called the yield sign. It separates your reactants from your products. This right here you saw in the ed puzzle. Whenever you see double arrows, this actually means that as you make products, your products can go back to form reactants. This is what we call a reversible reaction. Some chemical reactions are irreversible. Some chemical reactions are reversible. You'll be
like photosynthesis and ice.
Yeah. Ice melting would not be a chemical reaction, it's a physical reaction. Photosynthesis and cellular respiration, it depends. Oh, yes, you're right. But the idea of going back and forth between the two, they are two opposite reactions. You would have to have a specific catalyst to go to the other one. So, kind of. Fermentation, possibly, if you had the catalyst to go back. Use in place of this for reversible reactions. Now, one that's definitely reversible, I'll just write this out so you have it down, is this. This is the formation of ammonia. It's a very, very, very popular reaction. It's a simple reaction. It's a very popular one because ammonia is the starting point for fertilizer. Fertilizer is important because of farming and production of food. And so this process was made in the early 1900s to form ammonia, to form fertilizer. And so it is actually a reversible reaction. And because it's reversible, any reversible reaction, you can play with different aspects to make either more reactants or more products as a result. It means the reaction can happen infinitely. Yes, that is what that means. Unless you alter the conditions to stop making it reversible. And it goes once again in both directions. Solid, liquid, gas. That's what this stands for. So if you see parentheses and an S, an L, or a G, this is just telling you state of matter. So S would be solid, L would be liquid, G would be gas. So this is telling us just state of matter. AQ is state of matter as well. This is weird. AQ is something that I wanted to make sure to cover the lesson before we left so that you would understand this concept a little bit better. AQ stands for aqueous. What does that mean? Aqueous.
Water.
Agua, right? Water. Aqueous means dissolved in water. So for example, remember we took salt, we just threw it in water, we stirred it around. That would be an example of something that's aqueous. So if you see, and I do want to bring up like just how it looks in the symbol here, aqueous. You're going to see the little symbol down at the bottom. That tells us state. So if I see NaClAq, now that what that means to you is this is salt that's been dissolved in water. Whereas if you see NaCl with an S next to it, what are we communicating?
Solid.
This is just the solid NaCl. So if I take NaCl solid, I throw it in water, I get NaClAq. And so these little letters, they're always going to be to the bottom right-hand corner of the element or the compound. All there to tell you is the state of matter. Now in Unit 5, you're actually going to have to predict for any element or compound, within reason, basic elements and compounds, what their state of matter is going to be. And I already told you for this unit, you have to memorize the states of matter for every element on the periodic table. So if you forgot, this is the week to study that, because remember your test for my B days is going to be on Friday, because I only see you once next week and the quarter ends next Thursday. So it's going to be Friday this week to give you time. All right, bottom. If you see something at the top of the arrow, this is something that aids the reaction, meaning it's some kind of helper. First, we could add heat to a reaction. So if we add heat to a reaction, we either indicate that with a triangle means heat, or we write the word heat. One of the two. They mean the same thing. This means that heat is supplied to the reaction. PT, if I see an element or if I see a compound at the top of the arrow, so this can be either an element or a compound or an enzyme. This means we have a catalyst. An enzyme is a very complicated compound that's a protein. It helps the reaction go faster. Yes?
It's like the
On the top. In the top of the arrow. That means that's what is helping that reaction to go. And actually with photosynthesis, you need some kind of light in order for it to happen because of the light reactions versus the dark reactions. You need light for your plant to happen. But the idea here, just looking at what we have to know, is that if you see an element or a compound, which you'll see a capital letter there, at least one, or the name of it, that'll tell us that we have a catalyst. And a catalyst works to make a reaction go faster. It's a helper. Catalyst helps the reaction go faster. And for those of you who remember biology, it does this by lowering the activation energy. That is the definition of the catalyst. It lowers the activation energy, which means it lowers the energy needed for the reaction to occur. So instead of having to add more heat, we add something that lowers the energy requirement. And so these are just some symbols that you're going to see in passing in chemical reactions at this point. So, skeleton equation. The next thing is just to write down, and if you didn't already, write this down as an example of a skeleton equation. All a skeleton equation is, I don't think I can find it here, is that it is the identity of the reactant and products, but not necessarily the correct amount. Why do I say it like this? It could be the correct amount, it could be balanced, or it may not be. So a skeleton equation just tells us what are we making, but it doesn't tell us how much. It's like the ingredients. Right, it's like, I watched the show on YouTube called like a cooking switch or something. It's on Epicurious.
Oh, yeah.
And they'll give you like just all the ingredients of a dish, but they won't tell you the amount. And they're like, how am I supposed to make this you know how you're supposed to have like half a cup of flour or a cup of sugar or whatever, just flour, sugar, and then you have to figure out how much are the correct amounts. And so yeah, it's kind of like that deal. When you have a skeleton equation, you're being told the ingredients, but you're not being told the accurate amounts.
Chemistry is a lot like cooking.
It is a lot like cooking.
It's like you got all of these beautiful things.
Remember, you had the flip actually. Well, you weren't here last lap, but you had the flip after every 30 seconds. It was literally just like cooking. Sometimes when you cook like chicken, you have to like flip it after a certain amount of time. We did that with the pennies last class. Literally, a lot of the same techniques in chemistry are in cooking. It's like cooking, yeah. It's like when you do experiments, it's literally.
Yeah,
Exactly.
Because of the heat transfer.
Yes.
My grandma
A
never.
lot of chemical reactions are in cooking, especially if you're a baker. You have bread rising with yeast, and you have baking soda with the carbon dioxide makes the little holes in the bread. So it's a lot of chemistry.
Yeah, my grandma never really had an official job, but she was a really good cook. So we all in the family just called her the scientist because she knew how to make like the super
She had those good recipes. You have to know what mixes and what doesn't mix. And there's something called an emulsifier that takes like oil and water and allows them to mix when they're not supposed to. You get some compound called an emulsifier. Yeah, there's a lot of chemistry in cooking.
Some people could do it so good, but like the professional one, they know how to do it.
No, emulsifier. There's some.
Humidifier.
No, they're not the same. Yes. Go ahead. All right, so we're gonna go ahead and continue. What we have to do today, what we're actually getting to. So a lot of this is just intro terminology, but what we're gonna have to learn how to do in the next few minutes is how to take a skeleton equation and transform it into an equation that is balanced, meaning has the correct amounts. And so this is something some of you may pick up like this, and some of you may not, and that's okay. You're gonna have to work through it if you don't pick it up right away. But the idea is that we actually have to figure out how many irons would we have on each side, how many oxygens would we have on each side in a balanced equation. I know, Luke, you actually already solved that pretty much for this one, but that's gonna be the main goal for the day is we have to take a skeleton equation, which just tells us what we have, and figure out what are the correct amounts of how many irons, how many oxygens would make a balanced equation. And so this is I think this is probably going to be one of the final definitions because we have to get to actually what we're going to do with it. So a chemical reaction is described best by a balanced equation. And so the word balance means same amounts. What do I mean same amounts of? Same amounts of each element. So whatever element I have, I need to have the same amount of the element on the reactant side as I do on the product side. I tell you, the respiration actually has like 10 steps. You go through the whole process of what you have to do. And so you'll notice that there's the same amount of atoms on each side. So if you look at the chemical reaction that's here, the example, this is an example of a balanced reaction. What you're going to have to recognize is that these numbers in the front, this is a 2, this is an invisible 1, this is a 2. They're called coefficients. The same thing they're called. The number in front of a variable is called a coefficient. The number that's at the bottom here, H2, what fancy name does that have? H2. We know it's diatomic, but what is a number at the bottom right-hand corner? That has an actual name to it. Anybody who studies computers actually should know what that name is. Called a subscript. I think I learned it actually there first before I learned it in chemistry. A subscript is a number that's at the bottom right-hand corner. Superscript's the number at the top. So we are going to reference this number as a subscript, and this number in the front as a coefficient. That's what we're going to call them. In order to find out the total amount of atoms of an element you have, you're going to have to take the coefficient and multiply by the subscript. So in order to find out total amount, you're going to have to multiply the coefficient times the subscript. And in this case, that's just 2 times 2 for hydrogen, which tells me I have 4 hydrogen atoms. And you're going to do that on both sides of the reaction. You're going to take the coefficient, you're going to multiply by the subscript to figure out how many atoms you have. This is balanced because you've got 4 hydrogens here, and if you look at this side, you've got 2 times 2, which is 4 hydrogens. So they match. If the numbers match, it is balanced. That atom is good. Hydrogen is good. Oxygen, you've got 1 times 2, which is 2. And then on the other side, you've got 2 times, there's no number there. What's that number? An invisible 1. 2 times 1 is 2. Those numbers match. And we know that oxygen is balanced as well. And so if you have the same amount of all your elements on both sides of the chemical reaction, it means this reaction is balanced, and this is how it's played. Meaning it requires me to have 2 hydrogen molecules plus 1 oxygen molecule to make 2 waters. And so how are you going to do this? Well, the goal is you're going to have to transform those equations into balanced equations. I do have quick rules to balancing equations here, and I'm going to teach you a method to balance equations, but you may find that you don't have to set up a chart to balance equations. You may be able to do some of this in your head, and you may not. When I give you a method, it's just in case you're not able to do it in your head. These are the quick rules. This is what you will need to do to transform a skeleton equation into a balanced equation. You do not need to write this slide. If you turn to the back of your handout, I printed this one out for you. Hopefully it printed out okay. I know the printer or copier is kind of but if there's any words you need to fill in, please do. But other than that, I did print this out for you. So this is a quick guideline to how to balance equations. The first step is you're going to need to count atoms of each element on the reactant side and the product side. You may want to write this if you didn't already. You're going to figure this out by taking the coefficients and multiplying by the subscript. Equals amount of atoms. So if you didn't write that down, you may want to write that down now. Any coefficient you have times the subscript for that element is going to tell you how many you have of that element. Then this is going to be your responsibility. You have to alter the coefficients. You have to change the numbers in front of each element or each compound until the amounts of atoms on both sides of the reaction are the same. And so this is an example. Where you see the underlines here is the coefficient. It's in front of each element or compound. This is 4 times 1, that's 4 billion. This is 1 times 2, that's 2 oxygen. And this is 2 in front of Na2O. If you see a number, a coefficient in front of a compound, that coefficient has to be distributed throughout the compound to get the total number. Just like math, a lot of the words are similar. Distributed means the same as it does in math, meaning that if there's a 2 in front of here, that means there's 2 times 2 here and 2 times 1. Kind of make sense? So you'll notice I bolded and underlined this. Never, ever, 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 ever Meaning, don't say if you want to make Na plus O2 goes to Na2O, you're like, oh, well, sure, I could do this. I could just, make this 1 and 2. Oh, this does not exist. NaO2 does not exist. Because sodium has a +1 charge, oxygen has a -2 charge, and so if you say that you have 1 sodium and 2 oxygens, that means you've got Na with a +1, you've got oxygen 2 with a -2, so you've got NaO2 that has -3 charge, and it's no, not a thing. Because you've learned how to put compounds together, you should recognize you cannot change the subscripts. If you are being presented with Na2O, this is the compound you have. Those are the amounts. You cannot change those amounts. You can only change numbers in front of an element or a compound. Those are the only numbers you're allowed to alter when you're balancing equations. You also cannot do the following. You may laugh. You cannot do this. Oh, I need 2 oxygens? There! I got 2 oxygens. You cannot put a number in between the elements of a compound that wasn't already there. You can't do this. Not a thing. I know some of you will anyways. Hope you're paying attention. Change the subscripts. So if you change the subscript, you change the identity of that compound, basically. And so you have to leave them the same. You're being presented with the correct elements and compounds with their correct amounts. You can only change numbers in the front. You may only change coefficients in this process. If you change subscripts, just know you got it wrong. All right, so there are some tips and tricks, and we'll go back to these when we look at them in examples. So you don't have to write it down yet, but when we go to examples, I'll bring up each tip and trick as it shows up. First one, if you see an element appear more than once in a chemical reaction, balance it last, more than once on one side. What do I mean by that? If you look at this reaction, you've got oxygen shows up how many times on the product side? Twice. So that means wait to count oxygen until last. If you start with oxygen, you're going to potentially drive yourself up a wall, going back and forth trying to figure it out. This is a simple example. Some of them get more complicated, like your cellular respirations and photosynthesis. Those are more complicated reactions. But the same idea is in those actually. Biological reactions actually are very similar to this structure. You see it there. Oxygen appears in 2 different compounds. On the product side, we'll balance it last. If you see a polyatomic ion, oh boy. Balance it as if it were a single element. Now I am going to do you a favor, and on the test on Friday, I will have a list of the polyatomic ions for you. I'll put it on your test, just like I did with the electronegativity values, because I'm not testing your ability to know polyatomic ions, but I'm testing that you'll know what to do with them, if that makes sense. So I will be printing that out for you as on the back of the test as a handout to help. But if you see a polyatomic ion, and you should recognize when you have one, balance it as if it were a single element, meaning you need to recognize NO3, it's nitrate. So the way to think about this is you've got 1 NO3 on the reactant side, and how many NO3s do you have on the product side? The number in the subscript. You've got 3 NO3s in the product side. So if you see a polyatomic ion, it is going to be much better for you if you balance it together, if the same polyatomic ion shows up on both sides. Like I said, we're going to see this in examples as we work through. And I'll bring up these tips again to help out. Yes, ma'am. I do. It's this one right here. Do you have black paper? Okay. Could you just get the black paper along it, and then I'll do the rest. I just need to go back. Thank you so much. All right. So here we go. We're about to get to what we need to do. Example 1. And so you need to write down the example, and then I'm going to show you a way to do this, but if you already feel like you've got the idea down, beat me to the answers, and then check to see if you got them right or not. The first one, balance this equation. You've got BA plus O2 goes to BAO. First thing to think about, the arrow separates your reactants from your products. So the idea is that the amount of each element on the reactant side has to be the same as the amount of each product when you're done. I'm giving you kind of like, have you ever played bowling and you got like, you know, those bumper lanes? I'm giving you bumper lanes here. Meaning, I've told you where the coefficients are. Do you have to get, do those underlines have to be there? They don't. This is me providing bumper lanes to know these are the places where you change the numbers, where those underlines are. But they don't have to be provided. And when you get to the unit 5 where you have to complete your own chemical reactions, they won't be because you have to make the product properly. So, taking a look at this, just to go through a strategy. One strategy you can use is to count how many you have. So how are you going to count how many of each element you have? On the reactant side, how many barium atoms do you have right now? How do you figure that out? What's the number in front of barium? If there's no number there? 1. What's the number in the subscript if there's no number there? 1. Do you have to write the 1? How many bariums do you have on your reactant side? Right now?
1.
So far, so good?
Yeah.
Because the coefficient here is 1, and 1 times 1 is 1. So you can write it out, but like I said, you don't have to. This is just a strategy that a lot of people use, and you'll see it if you watch YouTube videos on it. This is a common strategy that's used to figure out how to balance equations. But you may be able to do it in your head. Just make sure the amounts are the same at the end. All right. O2. How many oxygens do we have in O2 to begin with? Because there's an invisible 1. 1 times 2 is 2. So that's just me counting how many I have on each side of the reaction. I've only done the reactants. On the product side, how many bariums do I have? 1 times 1, which is 1. Can 0 be an answer? You may want to write this down because there is more than 10% of students, I would say, that have put a 0. Like they're like, okay, 0. That means that that's not there. That means that it doesn't exist. Like 0 times 1 is 0. It means we make things up, right? 0 cannot be an answer. Then nothing exists, right?
That would be violating the law of conservation of mass. It's illegal.
0 equals 0.
Yeah, it does.
0 equals 0. But you're not saying what actually happened in this reaction in that case. Can 0 be an answer? No. You can't just.
Maybe. If
Right.
you think harder.
Nah.
No. Stop it. Don't put zeros in the front. I'm telling you, about 10% of students put 0 in the front last year. Don't do it. That's why I'm addressing it beforehand. Or you put 0 in the front. Don't do it. And 0, and I mean the number 0, not oxygen. I mean the number 0. All right. How many oxygens do I have in my product side to start with? 1, not 0.
Not 0.
Okay. So, we've already said the answer. I heard it. All right. So here we go. Are the bariums balanced right now? Yes. The numbers are the same. What's not balanced? Always seek for what's not balanced. Oxygen. So you look at oxygen to try to figure that out first. I've got 2 oxygens on the reactant side. I've got 1 oxygen on the product side. It makes the most sense to make smaller numbers into bigger numbers when possible. You don't really want to have to work with fractions. There are times where you can, but you don't want to have to work with fractions. You want to work with whole numbers when possible. So how would I change 1 oxygen to be the same as 2? So this is just a guideline. Change smaller numbers into 2 larger amounts. How would I change 1 oxygen to change this 1 into a 2. What do I need to multiply 1 by to get a 2? Is the math. 2. So you put 2 in front of here. Remember, you can only change numbers in front of elements or compounds. Compounds have to stay together. You can't break them apart. You're just getting the correct amounts. So now, well, I have 2 oxygens. So I'm just writing this down to keep track how many I have. But now that I put a 2 in front of barium oxide, what else do I have 2 of now? Right, because this distributes, right? So I now have 2 barium atoms. So what do I gotta do now? Now I gotta look at my reactant side. So you're gonna notice some back and forth until you figure everything out. All of your atoms have to match at the end. Your reactant amount has to equal your product amount. So how many bariums should I put here to make it equal to 2? 1 has to change to 2. I make this a 2, because 2 times 1 is 2. And this is just me keeping track of it. That's what you're seeing me do here. And then what number would go in front of O2?
1.
So I have to put that. It's implied. So your answer here, your correct answer here is 2 barium solid plus 1 oxygen O2 gas plus 2 barium oxide solid. Does the state of matter affect the amount? No, not at all. It could be written, but it doesn't have to be for any question. You may or may not see states of matter written. You should recognize barium is a metal. Metals are solids. O2 is always a gas at room temperature. And barium oxide is an ionic compound, and all ionic compounds, unless placed in water, are solids. These are their states of matter that we have studied. All right, so that was our first. I like to sort questions into level 1, 2, or 3. What level do you think this is?
1.
This is level 1. We always start at level 1. So this is as easy as a question as I could possibly give you. Level 1. We'll take a look at another level 1 before we move into level 2. And on the homework, I do also have it organized. Level 1, level 2, level 3. Level 3. Don't worry, the level 3s are optional. Level 1 and level 2 is always the level that'll be on a quiz or a test. Level 1 and 2. Good to move on? Right. Example 2, here we go. This is also level 1. Level 1. Yes, it's level 1. If you want to, once again, beat me to the answer, feel free. I'll give you some time to write this down. Beat me to the answer. If you feel confident in the technique, you can also wait for me. I would always try to solve the questions before my teacher. When I was taking both math and chemistry classes, just I had to get. Make sure you're writing down the example, and once again, see if you can try to figure it out before I do. Just checking. Remember, the idea is to count how many you have of each element, and then look for what doesn't match, and fix those elements. Make sure they match. It's the left side versus the right side of the arrow that you need to make sure matches. Your reactants versus your products. So that's why I write a dividing line here, because I know all of my elements on this side have to equal the amounts on the other side at the end. If you study biochemistry, by the way, you will study that in the respiration, some of the stuff are reversed. Yeah. Like, look through the steps of, for example, glycolysis, and then it'll tell you, like, if you look it up, some of the steps are reversible, some of the steps are irreversible. Meaning, sometimes you'll get a product that can go to reactants, and sometimes it won't. Glycolysis in the oxidation of glucose.
Like adding oxygen.
anaerobic processes without oxygen. You have to look at the reactions. Some of them are. Look for the ones with double arrows. Anyone that you see with double arrows is reversible. Yeah. Go ahead. But it's interesting if you look at that in your own time. All right. Here we go. So, first things first. You have to count how many you have. And like I said, you can do this in your head if you want. Or you can keep track by writing it down. I'm keeping track by writing it down just to show you where my mind's at as I solve the question. But even for Cambridge, if you were to just like write the numbers in the front and not show your work, they don't care because they're like, this is something you could do in your head. In an AICE class, which is a second year class. But that doesn't mean I expect you to do it in your head. That's why I'm showing you a method. So first thing, count how many of each element you have. How many chlorine? And yes, that is chlorine, not carbon iodine. Whenever you see C, which with what looks like a lowercase L, it is a lowercase L, not an uppercase L. So this is 2 chlorine. How many oxygens? Oh no. Oh no, no. How many oxygens? 3.
1, 4.
There's 3 plus 1. Oh no, I have it in 2 different spots. Was there something I mentioned about that? Put a star. If you have to add to get the amount, that means save it for, save it for last. Only once you've balanced the chlorine and you balance the hydrogen, then go back to the oxygen. I promise you, it will save time and headaches if you do it this way. Save it for last. If you had to add to get this number, because it shows up in 2 spots, save it for last. That's one of the tips I brought up. Save it for last. Okay, hydrogen, how many? Okay. So this is just me stating how many I have. On the other side, what I typically do is whatever order I wrote the elements in on the left side, I write them in the same order just to match it easier. So I'm going to write it on the other side as chlorine, oxygen, and hydrogen, only because that's the order I wrote it on the reactant side. It's just to compare. Your eyes sometimes move a little bit and you accidentally look at the wrong number. So, chlorine on the product side, how many? 1 times 1 is 1. Oxygen, how many? 2 times 1 is 2, right? Because of the 2 in the subscript. Hydrogen, how many? 1 times 1 is 1. And so you've got numbers here. Chlorine, and you could just start looking what doesn't match. As long as we don't start with oxygen, we'll be okay. And actually, even with oxygen, we'll be okay here. Chlorine, I want to change a 1 to a 2 to match each other. So do I change 2 to 1 or do I change 1 to 2? Always change the smaller number to be equal to the bigger number if possible. So always change the smaller amount. Just in the back. How do I change a 1 to a 2? What number do I have to put in the front here? Because remember, we can only change the numbers in front with the 2. So we put a 2 here. That changes the 2. But it also changes, right? Because this 2 now is for this whole compound. I'm saying I have 2 of this whole compound. So I have 2 chlorines. How many oxygens? 2 times 2 is?
4.
4. So me, I'm just crossing it out and writing the new amount. And then here, 2 times 1, that's why it's level 1. I literally only had to change one thing. So it looked a little bit more complicated than it was. This is going to be something, once the light bulb hits, you're going to be like, oh, this is easy. Hopefully the light bulb hits sometime between today and Wednesday. Like that light bulb turns on. Hopefully it doesn't go out.
Hopefully it doesn't go out.
Hopefully not. Not on the test.
You don't even have it.
But I always say that just to say that it doesn't click always for us at the same rate. Once this does click, it's either something you'll find really easy or something you'll find really difficult. But I'm trying to give you guidelines to help make it easy. It's like puzzle solving. If you like solving puzzles, you may like this. All right. So chemistry puzzle solving. Chemistry Sudoku. Almost. All right. The next one is first level 2. You're gonna be like, like what? Here you go. Level 2. Go ahead and write it up. I'll give you some time. If you feel comfortable, beat me to the answer. Level 2. Yeah. You said tone down. Somebody, I believe, is still out. Wait for the student not to come back. Yeah. It's like a puzzle. Yeah, you don't have to write the state of matter unless it's. I mean, you'll eventually need to. Eddie, this should be. You'll see a lot of times I won't write the state of matter at this point, like on the quiz, just because it lengthens the question. Not really, because in Unit 5 you are going to have to include states of matter. This is basically saying when I make these two solutions together, I make a couple of ions that are still in solution, but this solid comes together. I end up with a solid that's silver sulfate. And so it'll fall to the bottom when I do that chemical reaction.
Oh my god, check out.
All right, so I gave a little hint here. What separates a level 1 from a level 2? A level 2 is going to either have a polyatomic ion, or it's going to have some scenario where you have to go back and forth a couple times in order to solve it. And so you'll see what the level 2 questions look like. It is, once you figure out the trick, as I said, when the light bulb goes off, if you figure out what's going on here, you can solve this really simply. It just looks complicated. And so let's take a look, an inventory of how many we have of each element. Remember I mentioned when you see a polyatomic ion, this was one of the tips. You want to balance the polyatomic ion as if it was one thing. Don't separate it into the oxygen, because if you do, you're going to drive yourself up a wall. Or get lost in the applesauce. Things. You might get lost. So look for polyatomic ions. I see one here. It's the same here. That's important. They have to be the same on both sides. And I also see a polyatomic ion here. The one that's right there. See it?
I know, 3 or.
You look for those 3 oxygens or those 4 oxygens, and you're almost for certain that's a polyatomic. Yes.
At least I know that.
Okay.
You should not. You should not. That's what I'm saying to do. Don't do that. Don't do that. If you do, you may get yourself very confused very quickly. Because you would say you have 7 oxygens here and you have 10 over here. And how do you make 7 and 10 the same?
It's a lot like math.
It's going to get rough.
After the R with the arrow, the other side's gonna have like.
All right, here we go.
Right.
Silver. How many?
1.
1.
Think about
Now
it.
notice. Nitrate. How many?
1, 2.
Notice how I did it. I said that's a polyatomic ion. I'm keeping that together. I have 1 of it. Copper. How many? Sulfates. How many?
Wait, why is it 1 more?
Because of different.
This polyatomic ion, there's no parentheses here, which means that there's always only 1 of it. If you recall back when we were making compounds, if we didn't write parentheses, it meant we only had 1 of that polyatomic ion. You should keep
I get it.
nitrate together, keep sulfate together. It's going to make your balancing a lot easier. You can see it this way. I write the amounts the same on both sides, like I write them in the same order just to make sure that I'm comparing amounts correctly. Silver on the product side, how many? 2. Nitrate, how many? Just look for the number on the outside of the.
2.
Thank you. On the 2. 2 because of the number on the outside.
Yes.
2 nitrate.
Copper? 1.
Sulfate?
1.
No parentheses, so that means there's only 1. 1 of the sulfates. Alright, so now that we see it like this, start changing whatever needs to be changed. Start at the top, just to AG. I want to change that from a 1 to a 2. So notice here, you could either change the reactant side to the product side or the product side to the reactant side. you're not looking reactants to products or products to reactants. You're looking smaller to larger. You want to change the smaller amount to the larger amount. So whatever side that happens on. Silver, change 1 to 2. What number do I have to put in front of here to make that happen?
2.
Perfect. That changes 2 things, the silver and the nitrates. So I've now got 2 silvers, and I've now got how many nitrates? And because I wrote it all out, I can see that this is all done. Do you have to write all of this out?
No.
No. You can do that comparison in your head.
Should you?
You should, just to check to make sure you didn't make any mistakes, but you don't have to. It's a method to help. So this would be a 1, and a 1. So it looked, once again, more difficult than it was. All right. Let's take a look at another level 2. Try this one. It's kind of like a 1.5. Like a 1.5. It's a little bit simpler than the last one. I didn't include the stakes matter either. True. I was just like, let me put another example last night. So,
That's not that lazy. If it was up to me, I wouldn't even put anything.
see if you can beat me to the answer. I need a little bit of time. So what's a level 3? There's no tip or trick to help you. You're gonna have to work back and forth, and like the polys on ions don't match. There's one on one side and a different one on another one. There's no strategy to help you really. You just have to like kind of finesse your way back and forth to try to figure out the amounts. So logic problem. Level 3, if it shows up on the test, it will be extra credit. There will be one that will come up. What did we do with 2? I also put a few on the homework, but they're optional to do. I'll explain that when I pass it out. Extra credit on the test. If you want to do it in your homework, you can, but you don't have to do it. I'll tell you which questions they are shortly. They'll be labeled. This is not extra credit. This is like totally doable. Totally doable. All right. What if you don't write a chart? I was just gonna say, could we do this in our heads?
Yes.
Let's take a look at how we would do it, just with this example. So you would have to keep track of how many you have. How many calciums do I have here?
1.
1. How many calciums do I have here?
1.
So I know I don't have to look at that right now. Chlorines, how many do I have here?
2.
How many chlorines do I have here?
1.
So I know I have to look at that. Does that make sense?
Yep.
So I would change a 1 to a 2. A 1 to a 2. So what number do I put in front of here to make that happen?
2.
2. So I know my chlorines, you can put a little check mark there for yourself. You know, chlorines are good to go. Some kind of indicator for yourself just to remember. But now I have to check, oh, I have 2 of the sodium now, right? So there's only 1 right here. What would I put in front of here to make that work? If I put a 1 in front of there, 1 times 1 is 1. I need to have 2 sodiums at the end. So I would have to change this number to a 2. Do you think a pencil might be a good idea here, just like with Lewis structures? Oh, we just finished. I would say use a pencil. Do you agree? Use a pencil. I'll always have some in the front for you, but I suggest pencil for sure. Just finished. We did. Because there's 2 nitrates that actually already fixed this over here. And we already said calcium was good and we didn't change it. So you just check everything, make sure the amounts are the same. This is 1, 2, 1, 2. And yes, you could do it without writing out a chart. The chart's just to aid you if you need to look at how many you have on each side. All right, that was, yes. Yeah, okay. We're going to take a look at the other type of medium question. One that's a little bit complicated, but not too crazy. Meaning it's still at the level you can be assessed at. in a high school level class. Ready? Here's the other type of medium level 2 question. So this is the type of question you can still see on your test on Friday.
No,
Here we go.
2-1.
Balance this equation, level medium. See if you can once again beat me to the answer.
So it's like 2.5.
Similar, but not exactly the same. It would be, if it was the photosynthesis, it would be this.
I didn't know we were
Photosynthesis is the inverse of cellular respiration. So you could be given, I could give you this on a test, sure. AICE would. And ask you to balance it, right? They would ask you to balance this.
How?
possibly.
Why?
Balance
Sorry.
the two.
I'm erasing it, don't worry. I'm just saying that that's what it is. It's not outside the scope of reason to be asked. Yes.
See, in my life, there's a lot of things that can be outside the scope. And he is born.
Here we go. See if you can beat me to the answer. I'm giving you a few minutes. One.
Yeah,
That's like the world's worst phone number.
Hold on. Let me do that math in my head.
Wait.
I'm thinking.
You said 5, 6. The 5 and 6 are correct. And you said what was the number in front of oxygen?
No.
Right again. It is patterns, though. Yeah. I said it's like the chemistry logic puzzle. But that would be hydrogen peroxide. This is actually a reaction called a combustion reaction, also called oxidation because you're adding oxygen in. Combustion means that you are likely burning this to make this happen. This is a reaction of fuel. Your car engines do this all the time if you don't run electric vehicles. We're not doing types of reactions until unit 5, but this is a burn. Should separate everything because there's no polyatomic ions here, so everything should be separated. I do advise to write out a chart. I'm going to write out a chart for this one, but like I said, if you can do it in your head, I'm not going to require you to write a chart. Here we go. So then pay attention to what I do. Carbon, how many?
5.
Hydrogen, how many? Oxygen, how many? On the product side, carbon, how many? 1. Right? You can put the little ones there if you want to, just to remind yourself. Carbon is 1. Oxygen, or actually let's do it in the same order. Hydrogen, how many?
Hydrogen is
2 right now though,
yeah,
to start with. Oxygen, 2 plus 1 is
3, yeah.
3. Oh. You may want to do this just to write how many are in each compound as you go along. I've got 2 oxygens in carbon dioxide. I've got 1 oxygen in water. 2 plus 1 is 3. Because I had to add to get that amount, you should put a star. What does that star communicate?
Adding.
Do that last. Balance last. Because you had to add to get that number. And if you don't balance it last, I mean, you could try it. It's just going to be a struggle to solve. Yes, go ahead. All right. Here we go. As long as I don't change my oxygen until last, we're going to be okay. The first place to start, I'm going to start with carbon. I need to change 1 to 5. What do I put in front of carbon dioxide to make that happen? That changes it to 5. But what else does it change?
Oh.
It changes the oxygen, doesn't it? How many oxygens do I now have? 5 times 2 is 10. Plus 1 more? 11. All right. Ignore oxygen. You could just ignore oxygen until the end, but I just wrote it down. But ignore it. Go to hydrogen. How do I change 2 to 12? I have 2 hydrogens. Remember, smaller goes to larger. 2 times. So we have to put a 6 in there. Because we're multiplying by 6 to get to 12. Nothing yet, because it's not 11 anymore. Once I change this hydrogen to 12, now how many oxygens do I have? 6 times 1 is 6 here, but you had how many in the carbon dioxide? You had 5 times 2 is 10. 6 times 1 is 6. You have to add these two together. 10 plus 6 is? Make sure you're following along with this, because this is a medium level question. Does that 16 make sense for the amount of oxygen?
Yes.
You have now 10 oxygens in the carbon dioxide and 6 oxygens in the water. So finally, I've balanced my carbon, I've balanced my hydrogen. Only once you've balanced everything else, now look at oxygen. We need to change 2 to 16. What number goes in the front to make that happen? 8. So a little bit of math here. Are you allowed to use a calculator if you feel like you need one?
Thank God.
Yes. No calculator
How would
shade.
you
Bring a calculator Friday, just in case.
So it's 1, 8.
Yeah, but that's the math. How would you
The math? Do 16 divided by 2. It will tell you the number. If you need a calculator, sometimes you might. You never know. What if you get an extra credit question and the number's like 55?
Then I have a loop.
No, you don't. Not on a test. All right. So that was a medium level question.
What's a hard question?
Here we go.
Level
You
one.
want to see an example of what a level 3 could be? Here, let's take a look. So this is level medium / hard. This approaches level 3.
This is 2.8.
We're approaching level 2000.
Chemistry jump scare. I'm going to put the parentheses in front. This is the last question we're going to do. See if you can beat me to the answer if you like. If not, don't stress it. I'm going to go over it shortly. I'm passing out the homework though. So I'm passing out the homework now while I'm waiting for you to write down this last question. Only do the level 1 and level 2 questions, meaning the last page that says level 3 is optional but not required. It's just in case you want to take a look at what extra credit could look like. You said 2212? You have to get a little bit nifty here. And there is more than one correct answer. One with fractions, one without fractions. You can't have a fraction.
How do you have a 2? You don't have how do you have a 0? You don't have a 0.
There's oxygen on both sides. Approaching. All right, once I pass these out, then go ahead and solve it. All right, so the nitrogens are balancing. Alright, let's take a quick look at what we got going on. Calcium on the reactant side, how many?
One.
Should I keep the polyatomic ion together or not?
Yes.
The answer is no, because it's not on the other side. So break it apart. Nitrogen, how many do I have?
Two.
Two. 2 times 1. Oxygen, how many do I have? 2 times 2 is 6. Alright. Stop. Split up the polyatomic if the polyatomic ion is not on the other side. There's no NO3 on the other side. You have to split it apart. Calcium on the product side, how many?
1.
Nitrogen, how many?
2.
1.
No, because of,
1. Oxygen. 1 plus 2 plus 2. Fine. All right.
How did you get it? Oh, okay.
Put a star next to which element?
0.
So before you look at oxygen, fix nitrogen. How many nitrogens should I put here? 2. That changes my oxygen amount to 2 times 2, which is 4. But that 4 has to be added with the 1 in calcium oxide and the 2 in oxygen. So that's 1 plus 4 plus 2 is 7. So we've got the calcium's correct, the nitrogen's correct, and only the oxygen's not right. And we have a 7 and a 6.
-1.
Good morning, CIE. We hope you had a restful winter break. This is Destiny and Ileani. Please rise for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. And now, a moment of silence.
Just write down the answer for now. I'll do a couple more examples on.
You may now be seated. Here are your morning announcements. Attention CIE students, here are a few important reminders. Wear the appropriate school uniform. Your outerwear must be in the solid colors red, black, or white only. Class shirts are to be worn only on Fridays. School polos should be worn Monday through Thursday. PE uniforms can be purchased online